Right, hello there. After watching a couple of Raymond's videos, I come to an idea that maybe it's better to run the battery pack 12 volt to discharge and 4.2 volt to charge. So the idea is, I'm going to have a couple of relays. Now I'm not sure if you can actually see this. No, okay. For large marker side it is. I'm going to have a couple of relays. These relays are DP DT. Double pin, double throw. What this means is you have two lots of pins like that side by side. You will have one set of contacts that are normally closed, and here is the coil for triggering. So because you've got two pins, well, two rows of pins, you can trigger both the positive and the negative side of the batteries from parallel to series. So the idea is, the normally closed ones are the ones closest to the coil because it pushes them away. So you have to join those two together for normally closed. Now the battery will be here. I've probably got these terminal icons in the wrong orientation, but it's just to give a rough idea. Now what happens is, these are connected to the centre pins, right? So when the relays are not energised, they're in a normally closed position, so it sends current from there out of the joined pins which are now being joined to there to the next battery. That will give you the 12.6 volts. Now, when you change the relays and the energize, what will happen is the relays will trigger to the other pins. Now because they've energized to the other pins, this is putting the batteries in a parallel formation for 4.2 volt. So that one joins there, that one joins there, that one joins there, that one joins there. So we have solar positive in here. Right? So we have negative, positive, negative, positive, negative, and positive of battery. We have the positive battery wire running out to there. We then run this one down to the positive of that one. Then same again, positive down to the positive of this one. Now you would think that this would short out, wouldn't you? Because you're going positive to the negative of that battery. Well, what happens is, when you flick it over from this side to that side, it disconnects the join between the positive and the negative of the cells. So this no longer connects to that positive terminal, which means you're not shorting this battery out. So when you effectively do this, and this is the negative rail from the solar panel, this comes in, I'll do a little loop over to indicate we're not joining, and this goes to the negative of that battery, and the same again for negative of that battery, and as we go to the negative of this battery. In this formation we are at the 4.2 volt for parallel charging. So the next part of the circuit is you've got the energizer coils. Whoops, there goes my multimeter. So we have the energizer coils. What happens is that again, this comes off the negative side of the solar panel, like so. What we have off the positive side is, as we come down, we have a diode. No, not there. Sorry, the diode sits here. The reason we have this diode, there's no diode, that's just a straight link to the positive. We'll just do that there. Drawing's not my best point. So here we have the positive, here we have the negative. The reason we have the diode is, if we didn't, the charge from a battery would come up into the positive of the relay feed, and it would hold it in the 4.2 position. So the idea is, this side of the relays only want to be generated when we have solar power. So the solar power comes in, it sends the 5 volts, because my panels are only 5 volt at 2 amp a piece, so it sends the 5 volts into this relay, energizing it, flicks the contacts over to make it 4.2 volts rather than 12.6. The rest of the solar panel, what not being used by the relay, comes through the diode and into the batteries. Now, yeah, a lot of you would say that Li-ion batteries trying to charge at 5 volt is too much. So, in a different part of the circuit, I'm going to do what Raymond's done, and we have 4 of these step-down converters. And what will happen here is we will have the 12 volts in from a panel after the diode, we still need the diode because the batteries will backfeed through these voltage regulators. So what we do is we link them up. I'm not bothered about polarity to be precise at the moment, I'm just giving an indication to how it should be wired. Now, thinking about this more, you don't actually need that diode, because you could put, as Raymond does, diodes on the outside of these regulators. Now each one of these regulators will be set to 4.2 volt. They will be all linked together like so, and that one will loop over to the negative rail. So this then goes off to the battery, positive, the negative. Now, as the voltage of a battery becomes close to the input voltage, so this will be 4.2 plus a 0.7, so we are talking 7, 8, 9, so we're talking 4.9 volts out of these units into the battery. When the battery reaches 4.2 volt, it will stop taking current and actually just stay at constant voltage. Now everyone's going, yeah, this is unsafe, yada yada yada. I have had one of these units on a lithium-ion battery now in a bucket of sand, constantly powered for the past 2 months, maybe 3 months. Taking a battery out of the sand the other day, and it is perfect. It is at 4.2 volts. It has been now disconnected for a couple of days, and there's no sign of voltage drop for any damage at all. So they are safe to keep at a constant voltage. But the point is, as we will be using this for lighting anyway, they're never actually going to be constant at 4.2 volt. They'll always be dropping down and charging back up a little bit each time. So as this works, we can also link in. So if we have other ones of these and we put a relay on them, and this only has to be a 2-pin relay, well it's actually 4, you've got the coil and you've got the switch side. What we can do is, if you've got a wind turbine with its own battery, so we've got a 12 volt battery there linking into the step down controller. We have a diode to stop backfeed as usual, although that's probably not needed because we'll have the relay anyway. So this then goes into the relay and off to the battery. This side of the relay is triggered via the same system as this one. So when the solar power comes in, the relays trigger all your inputs from your alternative energy, be it water wheel, wind turbine and solar, can all be triggered when it's at 4.2 volt to charge a battery. Now 4.2 volt at a high ampage is a lot easier to get than 12.6 at a high ampage. So you can basically take for a water wheel. Now let's say you run this off your gutter. For the amount of rain we've had lately, that could be quite a good idea. If you just got a stepper motor from a printer to a water wheel that would work off the gutter, you could have had that running into a battery for storage. Now, if that gives out too low a voltage, what you could do is you could always use a step-up circuit to step it up to put it into a battery. So whichever way, you've got an alternative system to feed into this 4.2 volt when it's in its charging system. If all plans and theories go right, then you're looking at quite a good, efficient system. I hope you all understood and I hope you could follow. I did have a circuit I did online of this. It is rather complicated to understand. Just as like the drawing looks here, it's not very clear. But anyway, I hope this was all informational for you and I hope you all liked it.